My name is Jonathan Asher. Can you all hear me?
Yep.
Okay. Okay. I'm the Director of Design Technology at Zahner in Kansas City. We are a metal art and architecture fabrication company. We do building facades, we do building interiors, we do art pieces, both big and small. We work across a range of scales. We do small sculptures, we do small interior art pieces for the wall, we do stadiums. We do big stadiums, we do museums, we do cultural landmarks in major cities and small cities. Here's our headquarters in Kansas City, and we're primarily in the architecture, engineering, and construction company industry. We've been around for 117, almost 118 years. We were originally a sheet and metal contracting company. Now we're an engineering and fabrication company. We've flipped the structure of what we once were, where we were 10 people in the shop, in the office, and 100 people in the field. Now we are 100 people in the office and the shop, and we have 10 very specialized people out in the field installing our projects. We work all over the world on ranges of projects, so if you're ever in one of these areas, you can go check them out. Flip through a couple of them that you're probably familiar with. The Pritzker Pavilion in Chicago, Museum of Contemporary Art in Cleveland, the 9/11 National Museum in New York, De Young, San Francisco, Neiman Marcus, Boston, Cooper Union, New York, Burberry in Chicago, small chapel, St. Teresa's Academy in Kansas City, Urban Convention Center in Dallas, the Tubman Museum of Art in Roanoke, Tacoma Museum of Glass, Tacoma, Case Western University, Cleveland, Ohio, Hunter Museum of American Art, Chattanooga, Doha Art Wall in Doha, recently completed Cornell Gates Hall in Ithaca, and the Experience Music Project in Seattle. This is just a portion of the projects that we work on. If you go to our website and look at our portfolio, you'll see many more. This project is one that really refocused the company on computers and engineering in 3D prior to going to the job site. It also led to the ZEPS, the patented ZEPS process. It's the Zahner Engineered Profile Paneling System. And here you see some of the framing that goes underneath the skin, and one of our early digital models. So what do? We like to say we apply aerospace engineering for architectural applications. And we need them to build buildings like this. This is the Art Gallery of Alberta up in Edmonton, Canada. And a look at the digital model that we use to define the parts that are fabricated in our shop and then shipped to the site for installation. Here again, this was a ZEPS project, so it's the Zahner Engineered Profile Paneling System that's been discretized into unique parts, assembled in the shop to form these free-form curves and then shipped to the site for installation. One of the things that you see here is that we focus a lot on jigging. We spend just as much time defining the geometry and defining reference planes that we can use in our shop to help us put together these kind of free-form parts, these free-form geometry. And then you get these very curvaceous interior forms. Here's the Broad Art Museum in East Lansing, Michigan by Zaha Hadid. A look at the model where every skin is different. And that's one of the things that we have to deal with in our models is we don't have millions of similar parts, or same parts. We have hundreds of thousands of unique parts that go into all of our assemblies. So I'm going to talk a lot about power copies and how we build our power copies to be generative in nature so that they can adapt to local conditions in the model and still feed our shop with proper cut files. Here's a look at some survey information, reading the survey information into our model, modifying the model to match the survey information in context, and then assembly on the building. It's a beautiful building. Here's another project, Liverpool store in Mexico City. One thing that you'll notice, and we are working in Digital Project. Digital Project is essentially Catia V5. It's for architects and engineers and fabricators. So some of the images are going to look familiar. A lot of the screenshots are going to look familiar, but it's Digital Project, and we're in process of transitioning now to Catia and 3D experience. So this is going to get technical, and that's sent pretty soon. I'm going to talk about how we build our power copies, but what you'll see is basically Catia V5. Here's a screenshot showing where we've cut up that surface, placed our power copies, and defined them by ladders. Sent the fabrication information to our shop, and then brought them to site for erection. Here's the McCoy Federal Building in Jackson, Mississippi. Overview of the model. And in this case, one major advantage of working in 3D for this project was we were able to reduce redundancies in wall systems. We were able to pack more information and more systems into each wall panel, thus eliminating other systems. We incorporated more structure into our panels and reduced the studding and insulation and parts of the building that would traditionally be done by separate trades. Another image of the glass. Wall panels, all prefabricated, shipped to the site and installed. Emerson College, recently completed by Morphosis Architects in Los Angeles. This again was another ZEPS project, so here's the framing model. We left gaps between the panels so that they could be filled in the field. Here they are installed. And then they fill in those gaps and then skin over the top. This is a waterproof system, so the other benefit to filling those gaps in the field is we can maintain continuity for the water membrane. And one a little closer to where we are now, the Noisette Pavilion in Charleston, South Carolina. Actually, it might be North Charleston. There's the pavilion, Naval Memorial. If you're interested in going and having a look. I think Google Maps said it was an hour and 15-minute walk, but you can drive it in 12 minutes. So the Naval Memorial is the dot there. The pavilion is, can you get my mouse? Yeah, right there. And that again was modeled in the computer, fabricated at our shop, shipped to the field, and erected on site. And there's the pavilion. So, we work in the AEC industry. It's architecture, engineering, construction. For those of you who aren't familiar with it. The overall simplified project structure is that of an owner with having a contract with a general contractor and an architect. And then we as Zahner live in two worlds. We have a design assist field team that works with architects as a consultant, helping them define geometry, define rules for buildability, and work on the design. And then we have the subcontractor side that actually builds it, that does the engineering, does the fabrication, does the installation, and oversees the project management of our scope of work. Generally, we're subcontracted to either another subcontractor or a general contractor. Within architecture and engineering and construction, there's these different project delivery facilitators. These are concepts and software. There's BIM, Building Information Modeling. There's IDP, Integrated Project, IPD, typo, Integrated Project Delivery, or VDC, Virtual Design to Construction. That's primarily where we live. We'll take an architect's BIM model and then we'll detail it out to create a virtual design to construction model. And we'll carry that through scheduling simulations with different project management software. What software do we use? And this is engineering software. For 2D work, we'll use DraftSight or AutoCAD. For 3D work, we'll use Digital Project, which is Catia V5, essentially, and Rhinoceros and Grasshopper. Why do we use Catia? The primary, I guess above all else, is its surface control. It has, we all know, it is one of the best surface modelers in the world. And we deal with surfaces daily. Complex geometry, complex surfaces, freeform surfaces, ruled surfaces, surface rationalization for fabrication. We have to have that capacity. Other is the assembly logic, being able to build very large models, assemble very large models. The parametric modeling aspect, we build very intelligent parametric objects that are instantiated to maintain relationships within the power copy and can be edited after they've been instantiated. And the scripting. There's the VBA scripting, there's the Knowledgeware automation. We lean heavily on automation so that we can build these thousands of unique parts, similar parts but unique, and get them to the shop with the same kind of trust and level of and knowing that they are what they need to be. They are fabricatable. So how do we use Catia? We incorporate design for manufacturing principles, lean principles, and we've developed the ZMAP, which is the Zahner Integrated Modeling and Automation Process. The ZMAP is a way of building a master model, an integrated model that takes in Zahner inputs and external inputs, synthesizes them with power copies and other engineering constraints, and then outputs a communication model, a coordination model, a fabrication model, and an installation model all through the life of the project. So in our inputs, we've got wireframe geometry, dimensions, surface geometry, building level planes, grid lines, and they can compose our driver model. Reference models might be a structural steel model, concrete model, HVAC or MEP model, or an architect's design model. Those models all get pulled into our master model and referenced explicitly or implicitly in with the synthesis of our power copies to produce these other models. And with our communication model, we'll get architect's design intent. We'll get buy-in from them that we're going to build what they want to build. We're going to define our scope and communicate our scope with our subtrades or our client. We're going to create an engineering work breakdown structure and get constructability buy-in from different parties. Our coordination model is the next iteration of our master model, where we're producing structural center lines, getting solid geometry, incorporating the schedule, putting together a shipping strategy, producing shop drawings, and confirming engineering calcs. Fabrication produces a mock-up, usually. Robust bill of parts, QA/QC strategy, and shop directives. And then our installation model will include a shop erection sequencing, 4D simulation, or a field directive. It's also included, this process has included a standardization of our models. This is V5, so we still have a file structure that we need to maintain in the background. We've got our master product, the project all, and then we have the driver product, and where we have our surface geometry, our grids, our planes, our level planes, wireframe geometry. We'll have a fabrication product and then a reference product. The way this model develops over time is through an iterative cycle. So we start creating a level 1 model with simple, well, surface geometry, setting up the drivers, the level planes, and the grids, and importing a reference model, whether it's an architect's surface model or a BIM model, a structural model, whatever structural model we can get our hands on, taking in all the 3D geometry that's happened, all the 3D modeling that's happened prior to our entrance into the project, and putting it into one. We'll start then to build our smart power copies, and through automation, iterate them into the model, instantiate them into the model. And we'll build a light communication model with our building components. We'll continue to develop those power copies, putting more information into them, giving them solid geometry, updating perforations, putting on more detailed connections, re-instantiating them to get a coordination model. And there we're checking clash detection, more constructability buy-in from outside parties, from inside parties. We'll continue to develop the power copies. We'll put fabrication information into those power copies, re-instantiate, and eventually get to a fabrication level model. If we move forward into installation level model, we'll start to input the field directives, shop directives into our model. If we're sharing the model with our shop, which we do on occasion, or when we're giving our model to our field superintendent. So the installation model is the outcome. And within this iterative development process, there's all kinds of outputs and all kinds of inputs that come in to affect our power copies, that affect our design, our surface model, our driver model. So the feedback loop is an integral part to this iteration, to these iterations. Within the process, there's the design phase, there's the execution phase, there's the divergent phase and the convergent phase. All the while, we're working from gathering information through closing out the project. And if you take that idea of design phase and execution phase and you unroll the iterative process, you get this more linear project timeline where we are building our models, verifying our models, iterating through our models, and outputting work breakdown structures, structural centerline models, solid geometry, bill of parts, shop directives, field directives, and eventually an archived model, VEC constructed model. So what are the techniques for building these power copies and these integrated models? There's 5 parts essentially. There's the contextual driver model. There's the generative power copies. There are parametric power copies, automation that are knowledge patterns generally, that integrate or that instantiate our power copies, and they all feed in to make the integrated master model. So the contextual driver model, I mentioned it earlier, it's design surfaces, it's level planes, it's building and site grids, structural wireframes, boundary surfaces. And an example of that is here, where we see surface geometry for the interior of a theater. And you can see the control curves. You've got points and lines, and these lines control tangencies of the splines that define the geometry of the surface. We have level planes that slice up the surfaces that we use to support, to reference our power copies with. And other geometry, stair geometry, that define boundaries for our panels. We have generative power copies. And these power copies contain knowledge patterns, rules, actions, and reactions. These generative power copies they support all of the other power copies that need inputs when they're instantiated. This is my favorite. This is the Smart Divide. This is a power copy that takes in a curve or a multi-domain curve as an input. The knowledge pattern runs, and it it produces a set of points and a set of planes. Now, Catia already includes this functionality. It's the point and plane repetition tool. But that tool doesn't output a list of geometry. It just outputs elements, geometric elements, planes and points. Yes, they have formulas, but there's no list. So processing those points with power copies would require manual input. Here's the code. There's inside that knowledge pattern. That's all of it. It's really not much. But this little bit is probably the most important part because it's defining how it's going to subdivide the line. Is it going to do it by spacing? If so, then we're going to change the count of our for loop that divides the curve, and we're going to change the spacing. If it's by segments, we're going to use a different way of subdividing that curve. If it's by target spacing, different formula. Max spacing, different formula. And by chord length, different formula. And the output are lists of geometry. So the way we link our generative power copies is through lists. One power copy builds on top of a previous power copy that can be used as a knowledge pattern input. So here we have a points list, a planes list, a segments list, and then a join segments list, which, okay, join segments list is just one curve. And here's our parameters that shows how we're dividing the curve. We've got the divide type, spacing, segments. Are we generating planes? It's a Boolean question. What is the orientation of the planes that we're creating? Are we going to generate line segments between points that we've subdivided on the curve? What's the distance from the start that we're going to start our subdivision, and what's the distance from the end where we're going to end our subdivision? And then at the bottom you see there's some reporting parameters that are going to tell us how many segments it's created, how many points it's created. And here we see then how those power copies are, where they've been placed in the model. We have a smart divide power copy that defines the horizontal levels, the level planes, and then we've linked those level planes to a smart intersections power copy. So we built another power copy that builds on top of the previous power copy to create these intersections. Those curves then will get fed into another power copy that's going to process the curves and produce more points, more planes, panels. And we've created a library so that we can reuse all of these generative power copies so that the list generation can live on from the project beginning to the project at the end. Here we've got perforations, planes, points, profiles, projections, serrations, sketches, skin panels, skin pattern generators, the smart divide. We've got a handful of different types of smart divides. Some produce circles, some produce squares, some work on multi-domain curves, some work on closed curves. We have snap block power copies, sort power copies, split power copies, stair profiles, sweeps, tags, teeth, and that's just P through T. We have a range of power copies that get reused on every job. Using the output from the generative power copies, we build these parametric power copies. These power copies are largely composed of parameters, geometry, rules, actions, and reactions, and knowledge patterns. Here's an example of a parametric power copy. It's a splice plate. It's a splice plate, and you can see the driving control parameters at the top. We have naming parameters, and then we have dim parameters, dimensional parameters. We've embedded a bunch of rules and reactions inside that power copy, and a knowledge pattern to define the geometry inside the power copy, to make it intelligent so that when it's instantiated, it can generatively define its own internal geometry within defined constraints. Here we've changed one parameter, we've made it longer. The top length of that plate has gotten longer. There's the previous. There we changed the top plate length, and the whole spacing updates. Here we changed the middle length, and the whole spacing updates. And the way that we can get these power copies to behave this way is by embedding generative power copies into the parametric power copies. So here we've got a rule, generate holes, that is essentially performing the smart divide task internal to the power copy to create the holes based on set spacing rules. So in this case, we've set the divide type to max spacing. We've given that max spacing 135 millimeters, and we've given it a circle diameter. Bringing those two together is the automation and instantiation piece. So here we have knowledge patterns that are generally embedded in power copies, and they instantiate power copies. We also have actions that in products that instantiate document templates, but I'm going to focus mostly on power copies that instantiate power copies. Here's an example of a simple power copy. It's a knowledge pattern, an empty geometric set, and some parameters. And this instantiates power copies, that's it. You set up inside your driver model, your master model, you set up a part with all of the inputs that have been placed into lists, and then you instantiate this power copy into that part using the lists as input, run the knowledge pattern, and it's going to instantiate your power copies. This was a big deal for me. I know it's easy to set parameters for UDFs when you instantiate through a knowledge pattern, but it took a very long time to figure out how to set parameters for power copies when you instantiate through a knowledge pattern. Maybe there's an easier way. The only way I could figure out to do it was to take the power copy that you're instantiating through code, insert it into a list, and then set the attributes of that object from the list. So grab it right out of the list and start setting attributes. With that framework, we're able to instantiate thousands of power copies at a time and set their parameters so that each one is unique, even if it's just the name, changing the name. Because when you change the name and it has a different surface and a different plane, it's going to take on different geometry. Now it's a unique element in the model that we can export. The real power in all of this, though, is nesting instantiators inside power copies to build very generative assemblies, essentially, within a power copy. Here is a vertical power copy assembly. Inside that power copy, there's a reaction that extracts edges. That's in VBA. There's a power copy to generate lines and surfaces for inputs. There's a power copy to instantiate steel splice plates, a power copy to instantiate aluminum channel extrusions, and a power copy to instantiate aluminum brackets. You instantiate this power copy into the model, you run all the instantiators, and you get a very sophisticated assembly. And here's the update sequence then for this particular power copy. When you instantiate via a knowledge pattern, you switch the run instantiators parameter to true. Switching that parameter triggers a reaction. The reaction will trigger, well, first I should say, when it's instantiated, the change in geometry, the change in inputs is going to trigger the VBA action. That's going to move some lines around and extract some edges. Then, after the run instantiators parameter has been triggered, it's going to set the reaction to update the knowledge pattern for bisecting lines. The bisecting lines knowledge pattern is going to produce some surfaces, some boundary surfaces, some input lines for the rest of the power copies. And it's going to produce a list. And that list is what the other instantiators read. After that knowledge pattern is run, it's going to update the splice plate instantiator. It's going to update the removed surfaces. Then the removed surfaces reaction is going to pull surfaces out of the instantiated power copies, and so it can be used as an input for the next set of instantiated objects, which is the brackets. And then we'll get finally the vertical extrusion instantiator is going to update. And we have an instantiator for that power copy. So the instantiate vertical assembly power copy instantiates all of those power copies, triggers the knowledge patterns to generate the parts. And when you run that power copy, you get a model like this, where you've got splice plates, now splice plates that can do multiple things and accommodate kind of any geometry. You've got these vertical extrusions that are reading the perpendicular bisecting surfaces to produce the miters. And inside of each one of those power copies is the fabrication information that we can extract from the model and send to our shop. So no two parts are alike, and that's okay, because we can model it and we can manage the model and we can send it to the shop.
One question, at this stage here, all the parts are inside one part?
Yes.
Or still at the conceptual? It's not a detailed level assembly.
It's not a typical Catia assembly. Right, not at all. These assemblies are power copies that live inside one part. So it's a different structure, it's a different way of working. If we were going to do it more conventionally Catia, we would definitely build document templates and instantiate these parts. The difficulty for us doing that is we would have the management problem of dealing with thousands of unique parts in the model, and we found that Catia v5 isn't very good at managing thousands and thousands of unique parts. This way, doing it this way, yes, our files get very large, but we can manage those files in our larger model assemblies with relatively more ease.
I totally understand. And also in terms of performances, I'm sure that the iterations was much faster.
Much faster. And this is a view of that in the model, where we've got our structural model, which is very large. It's not our model, that's an imported model. And then our more detailed assemblies in parts. And that's part of the art of building these models, is where do you subdivide? Since a part isn't really a part, where do you draw the line between parts? How big can you build a part without it getting too big? But how much work can you do? Because you're automating, you don't want to do too much work building too many separate parts to throw 3 unique parts into it. So these are the instantiator power copies. And we have libraries for these. And this is just project specific. This is for the Edmonton downtown arena that we're building that we're fabricating right now. We haven't started installing yet. For the Edmonton Oilers hockey team. That leads us to the integrated model. The integrated model, where we have our inputs, our driver model, we have the external inputs, and we have our power copies that get into the model through our automation. Here's a quick slide of the Edmonton Oilers hockey arena that is going up now. And here we've done, our scope is the exterior of the building, the skin, but we're also engineering the curtain wall. So we built a model of it's a unitized curtain wall. We built a model for every panel, every glass panel on the building. Those units were exported as step files, and they're being fabricated from the model in Toronto. So examples of the integrated master model. Here's the University of Southern Indiana. Showed a couple slides of this. This is from Malcolm Holtzman Architects in New York. They wanted to build this very curvy feature wall, and they didn't have a lot of money to do it. And they gave us a model. This was their model from Sketchup. If you're unfamiliar with Sketchup, it is a modeling software for the average Joe. I don't know if you can build from it. I'm sure some people have successfully built from it. But we don't build from SketchUp. So the first task was to take these surfaces and put them into our model them so that we could build from them. And this is clearly just not buildable out of metal. Or maybe it is, but it's out of our range of expertise. So we built these driver surfaces again, and since the architect didn't know what the surface should look like, we put into the model the capability to sculpt the surfaces. So here you can sculpt the surface with the points and the lines to get based on tangency of the splines. And it was a very iterative process, even sculpting these surfaces with the architect so that it could get just right. We also had to sculpt it to avoid other trades. We had to sculpt it for the structural steel. We had to sculpt it for the staging. We had to sculpt it for the seating. We had to sculpt it for these balconies. So there was a process of first setting up the surfaces so they could be malleable, and then actually manipulating them with the architect and communicating the changes. Once we had the surfaces, we set up these level planes, start slicing up the surfaces, and then we built this first power copy that would produce this chevron effect and reflect the geometry of the surfaces. Instantiate them in the model, and you get a non-buildable but very expressive surface model. So we can show this to the architect and say, this is what we're thinking. We're going to build something like this. Does this fit within your design constraints?
Jonathan?
Yes.
4 minutes left. Now, if you thinking about
4 minutes left. I might need a couple more minutes than that. I'll go quickly then from here on out. We build a light surface model that is an approximation of the chevron surfaces that includes developable surfaces that can be unrolled and fabricated. Put that in the model because we can't build those free-form surfaces. And we give this to the architect and say, this is something we can build. How do you like that? Good. And then we put the perforations in. And we put the notches out for the lighting. And we instantiate this throughout the model. Here's a XML I'm going there now. And that power copy includes the unfolds of each one of those surfaces. The unfolds that have been rebuilt so that our shop can consume the geometry. Here's one unfold, and here we've got more generative power copies that do that subdivide the splines, the boundary splines, and that produce the perforations. So the perforations are all done in a flat. The geometry is created in 3D. It's unfolded to a flat surface, a plane. The perforations are generated and then remapped back into 3D. It could have been done in 3D, but this was just, this was easier. Those files get exported to 2D and the shop. There's a view of the fabrication model. A stack of unfolded parts in the middle. It may be worth having a look at the model if we can get into it real quick. The other thing to note here, I know architects and fabricators, and actually the construction industry, I should say, generally has half-inch tolerances on a site, on a job site, and this model was built with really zero tolerance. I know that's a fallacy, but the tolerance, these surfaces touch, so it's hundredths of a millimeter tolerance. The model was given to our shop guy, our field guy. So our field guy has the model. He's looking at the notes in the model to assemble this, and everything fit. So there's the model.
Jonathan, that'd be an example of design assist.
Yes, it wasn't a design assist contract, but we were placed in a role of design assist because the architect needed help. To build what they wanted to build, we needed to help them. This was the one drawing that they had for fabrication. Each panel had 5 dimensions, and then we built a special table to jig these panels up for assembly. Here's a spreadsheet showing those 5 dimensions and the special table, and one of our guys welding it up. Here's a finished panel. Nice thing about this view is you see the stacks of parts in the background. We built a mock-up because these are all backlit, so the architect wanted to see the backlit panels.
Dr. would you like to take a last minute for some questions?
Let me just go real quick. I'll fly through some of this. There's one project I want to show, and that's Peterson Automotive Museum. Since there are a lot of car people in here, car designers and engineers, this is a car museum in Los Angeles that's designed to look like a car in a wind tunnel. Our scope is this exterior ribbons. Show some of the fabrication parts for these. No two are the same. There are a couple hundred of these ribbons. We've got horizontal fins, vertical fins, skins. These are document templates, so these are instantiated into the model with the drawings that go to the shop. We've got a great little time lapse of our shop assembling these panels. There are some non-lean activities in this video, I know. I picked this video though because it's exciting. It's got a lot of stuff happening. This was the day when we shifted panels. So you saw one was perpendicular, now it's just been shifted. There's lunch. And it's great to see the process of assembling one of these panels. We built a mock-up. We invited the architect and the owner. We did a shipping study for each one of these. So the process is these are fabricated, set on trucks. The trucks go to a yard and wait until they're delivered to site in the installation sequence. They're lifted to the top of the building where they're staged and then set on the building. These are built within 1/4 inch tolerances, which is actually it might be 16th inch tolerances. And there's the product. There's what it will look like. Those installation photos a few days ago. So where are we taking the future? We're going to keep working on interesting jobs. This is going to be the second largest aquarium. It's down in Brazil. We're working on interesting surfaces. This is the tessellate surface that is responsive. We're working with just material studies, R&D, to get different surface effects based on forming. And we're building a suite of software solutions for the web that bring our shop to architects and to the public. So here you can create this image wall online at the shop floor website. And the great thing about this is you get cost feedback, so you can see what the cost is to engineer these systems. That's shop floor. Thank you.
Are you available for a couple minutes after?
Absolutely.
Absolutely. I'm going to give you a speaker gift. Thank you very much for a great presentation. You had a big crowd, and I think you delivered a great presentation. Thank you. So you pretty much you're free to go to lunch. You know, there are a lot of options for you guys this afternoon if you're interested in the KVE track. So 11:15, there's getting started with Knowledgeware, 3D experience. And then at 3 o'clock, you need like split personalities because we have a hands-on presentation to create threads in the training room. There's another hands-on presentation to experience building process templates. And there's another presentation about understanding the difference between V5 and V6 with the Knowledgeware suite. So, anyways, there's not enough of us to go around. Have a great afternoon.